There's a question that seems almost childish at first, so simple you might feel embarrassed to ask it out loud. But hidden inside that simplicity is one of the deepest, strangest puzzles in all of human knowledge. It's a question that has challenged every physicist for more than a century, a question that defines the limits of what we truly understand about the universe. What exactly is spacetime? It's a term we all hear constantly, news articles mention it, scientists talk about it casually, and we use technologies every day that depend on it working perfectly. GPS relies on it. Black hole photographs rely on it. The very fact that starlight bends, that the universe expands, that time can stretch and twist, every bit of it comes from this mysterious thing we call spacetime. And yet, the more closely you look at it, the more unsettling the truth becomes. We don't actually know what it is. We can measure how it bends. We can calculate how it curves. We can watch ripples move through it from black holes colliding a billion light-years away. But when we ask what spacetime is made of, everything we know collapses into uncertainty. To understand how we reached this strange place, we need to go back to the beginning, not the beginning of the universe, but the beginning of the idea. And that story starts in an unlikely place, a small office in Bern, Switzerland. In the year 1905. At that time, Albert Einstein was not a professor, not a famous scientist, not the man whose name would become synonymous with genius. He was working as a patent clerk, spending his days reviewing applications for electromagnetic devices and his nights wrestling with questions that no one else seemed to notice. He was 26 years old, an age when most people are still trying to figure out their careers, and yet in that single year, he produced 4 papers that reshaped physics forever. One paper proved atoms were real. One helped establish quantum mechanics. And 2 of them introduced something called special relativity. Special relativity sounds intimidating, but the core idea can be stated in a single sentence: the speed of light is always the same for every observer, no matter how fast they're moving. At first glance, that idea sounds impossible. If you're on a train moving 100 kilometers per hour and you throw a ball forward at 20, someone on the ground sees the ball move at 120. That's obvious, speeds add. But light refuses to play by those rules. Imagine a spaceship flying at half the speed of light. You shine a flashlight forward. Your intuition says the beam should travel at 1.5 times the speed of light. But it doesn't. Anyone watching you sees the beam moving at exactly the speed of light. And you, sitting inside the ship, also see it moving at exactly the speed of light. That sounds impossible. There's no way both of those observers can be right, unless space and time themselves are bending to make it true. And that's exactly what Einstein realized. Time slows down for fast-moving objects. Distances shrink along the direction of motion. Clocks tick differently depending on how you move. Space and time, once thought to be separate, rigid, absolute, melt into a single fabric, spacetime. And on that fabric, nothing is fixed. Everything bends. What makes this even more astonishing is how real these effects are. They're not illusions, not tricks of perspective. We've measured them with particle accelerators. We've flown atomic clocks around the world and watched them tick at different rates when they return. We've seen unstable particles live longer simply because they're moving fast. There is no universal now. There is no cosmic clock. Time is personal. And space stretches with motion. Already, Einstein had shattered the intuition humans built over thousands of years, but he wasn't finished. Because special relativity didn't explain gravity. That missing piece would become the most difficult, most beautiful, and most revolutionary idea of his career. And it began with a thought so simple you could imagine it yourself. Einstein pictured a man falling off a roof. During the fall, the man would feel weightless. A hammer falling beside him would hover at his side. His perspective, falling freely, made gravity disappear. And Einstein realized something profound: falling under gravity feels exactly like floating in empty space. Acceleration and gravity, he concluded, are the same thing. That single insight became the seed of general relativity, the theory that would take him 8 exhausting years to complete. And when he finally published it in 1915, it revealed gravity not as a force, but as geometry. Massive objects curve spacetime, and other objects move along those curves. Planets don't orbit the sun because they're being pulled, they orbit because the sun bends the fabric beneath them. To visualize it, people often use the rubber sheet analogy: a heavy ball creates a dip, and smaller balls roll toward it. But the real universe isn't two-dimensional. It isn't a sheet. It's a four-dimensional fabric that curves in ways our minds can barely grasp. And yet the math works. It explains Mercury's orbit. It explains the bending of light. It predicts black holes and gravitational waves, decades before they were observed. The world watched Einstein's predictions come true in 1919 when starlight shifted during a solar eclipse exactly as his equations said it would. Overnight, Einstein became a global icon. But even then, no one understood how far this idea would go. Because buried inside Einstein's equations were predictions so extreme, so counterintuitive, that even he refused to believe them at first: predictions of mass collapsing into darkness, predictions of singularities, predictions that space and time could break. And as the decades passed, physicists discovered those predictions weren't just mathematical curiosities, they were real. Black holes exist. Singularities exist. Spacetime can ripple. It can tear. And at the edges of our understanding, it fails entirely. And so the question returns: what is spacetime? We know how it bends, how it curves, how it influences matter and light. But what is the substance of the fabric itself? What lies beneath the equations? What is the universe made of at the deepest possible level? That mystery is where our story truly begins. Einstein's vision of spacetime was elegant, almost too elegant. A smooth, continuous fabric stretching across the universe, bending under the weight of stars and planets, shaping every motion, every orbit, every beam of light. And for years, that picture seemed complete. General relativity explained almost everything. It predicted things no one had imagined, and every prediction that could be tested came true. But then something strange began to happen. The equations, as precise and beautiful as they were, also predicted places where they stopped making sense. Places where the math collapsed into infinities, dividing by zero, curving space so violently that the laws of physics simply broke down. These weren't just mathematical oddities. They were predictions of real objects, real events, real places in the universe. The first hints of this came from a solution to Einstein's own equations, discovered in 1916 by Karl Schwarzschild, a German physicist solving complex mathematics while literally serving on the front lines of World War I. In the mud and cold of the Russian front, he somehow managed to write down the first exact solution to Einstein's brand new field equations. His solution described the spacetime outside a perfectly spherical mass. But buried inside that solution was a radius where the math behaved strangely, a point at which certain terms blew up to infinity. Schwarzschild didn't know what to make of it. Einstein didn't either. No one did. This radius eventually became known as the Schwarzschild radius. Today, we call it the event horizon. At first, physicists ignored the weirdness. After all, the sun's Schwarzschild radius is only about 3 kilometers. Earth's is less than a centimeter. These strange infinities only showed up far inside real physical objects, in regions the vacuum solution wasn't meant to describe anyway. So they shrugged it off. A mathematical artifact, nothing more. Even Einstein dismissed it. He thought nature would prevent anything from ever collapsing to such an extreme. He was certain that matter had some inherent resistance, some pressure, some quantum force, that would stop a star from shrinking beyond that point. He believed singularities were signs that mathematical approximations had been pushed too far, not predictions about the real universe. For decades, physicists agreed with him. But nature had other plans. In 1939, J. Robert Oppenheimer, the same Oppenheimer who would later direct the Manhattan Project, and his student Hartland Snyder decided to take Einstein's equations seriously. They modeled what would happen to a massive star at the end of its life, after it burned through all its fuel and could no longer hold itself up. What they found shocked the scientific community. According to their calculations, once the collapse began, nothing, not gas pressure, not electron pressure, not neutron pressure, could halt it. The star would shrink past its Schwarzschild radius and keep collapsing. Not just into a dense ball, not into a tiny sphere, but into a singularity, a point of infinite density and zero volume. This wasn't a trick of the math. It was a genuine prediction. Einstein hated it. He thought they were wrong. He published papers arguing against the idea. But the math was airtight. The conclusion was unavoidable. Black holes weren't science fiction. They weren't metaphors. They were real. And even worse, singularities were real. At those points, the curvature of spacetime becomes infinite. Every known law of physics fails. Time itself ends. Oppenheimer didn't call them black holes, that phrase wouldn't be coined until the 1960s, but he understood what they were, regions where spacetime collapses so violently that nothing can escape, not even light. It took decades for the scientific community to fully accept the idea. But as telescopes improved, evidence mounted. In the 1960s, astronomers discovered quasars, brilliant, distant beacons so bright they outshone entire galaxies. The only explanation was matter spiraling into supermassive black holes millions or billions of times the mass of the Sun. Then came the theoretical breakthroughs. In 1965, mathematician Roger Penrose proved that once a star collapses past a certain point, singularity formation is unavoidable. Stephen Hawking extended this work, showing that singularities weren't just possible, they were inevitable in general relativity. The Big Bang itself, if you run time backward, ends in a singularity. In other words, Einstein's beautiful theory predicted its own breakdown. And then Hawking shook the world again in 1974 with something even stranger: black holes. Despite their name, aren't completely black. They glow. The reasoning behind Hawking radiation was unlike anything physics had seen before, a bridge between general relativity and quantum mechanics. Two theories that normally refuse to cooperate. Hawking realized that quantum fluctuations near the event horizon could allow particles to appear in pairs, one falling into the black hole, the other escaping outward. To an observer far away, it looked as though the black hole itself emitted particles. And because energy cannot be created for free, the escaping particle stole mass from the black hole. Black holes evaporate. Slowly, but surely. A black hole with the mass of the Sun would take far longer than the age of the universe to evaporate, 10 years. But smaller black holes evaporate faster. Much faster. A black hole the mass of a mountain would evaporate in a fraction of a second, releasing an unimaginable burst of energy. This revelation created a new problem, one even stranger than singularities. The information paradox. Imagine throwing a book into a black hole. Everything that makes the book what it is, every atom, every arrangement of ink, every word, is lost behind the event horizon. The black hole emits Hawking radiation, but the radiation is thermal. Random. It contains no trace of what fell in. When the black hole evaporates completely, all the information about that book appears to be gone forever. Quantum mechanics says that's impossible. Information must be preserved. Always. The universe is allowed to scramble it, twist it, hide it, but never destroy it. General relativity didn't seem to agree. For the first time, physics had arrived at a crossroads where two pillars of science, quantum mechanics and general relativity, were making contradictory predictions about the same phenomenon. Both theories had been tested to extraordinary precision. Both were right in their own domains. But they could not both be right everywhere. Something was broken. And whatever was broken had to do with the very nature of spacetime. Because if a black hole can destroy information, then spacetime itself is somehow eating the fundamental fabric of reality. And if it can't destroy information, then something about spacetime, its geometry, its boundaries, its structure, is deeply different than we think. Either way, our understanding is incomplete. The more deeply physicists examined spacetime, the stranger it became. Everywhere it appeared clear and continuous, like smooth fabric, it also hinted at hidden complexity. At the smallest scales, relativity predicted smoothness, but quantum mechanics predicted granularity. Relativity said spacetime could bend and curve, but quantum mechanics said nature comes in discrete packets, not continuous flows. Some theories proposed that spacetime is woven from tiny loops. Others argued it's made from vibrating strings. More radical ideas suggested spacetime might not be fundamental at all, that it emerges from something deeper, like temperature emerging from atoms jostling inside a gas. As each new idea emerged, one thing became clear. Spacetime is not what it appears. And every mystery, from black holes, to the Big Bang, to quantum mechanics, seems to point toward the same wall. A limit in human understanding. A doorway we have not yet opened. But before we can pass through that doorway, we need to understand something crucial. Even though spacetime is mysterious, we rely on it every day. Not abstractly, not indirectly, but literally. Your phone, your navigation system, your internet connection, none of these things would work without Einstein's equations. Right now, whether you realize it or not, you are using spacetime. And that is where our story turns next. Right now, without even thinking about it, you are depending on Einstein's ideas about spacetime simply to know where you are. Every time you use GPS, whether you're navigating a city, tracking a package, or watching your food delivery inch closer to your door, you're tapping into a delicate dance of satellites orbiting Earth. Each of these satellites carries an atomic clock, ticking with extraordinary precision. But here's the strange part. Those clocks do not tick at the same rate as clocks on Earth's surface. Because they are farther from Earth's mass, time passes faster for them. Because they move quickly in orbit, time also slows down for them. These two competing effects, one from general relativity, one from special relativity, don't cancel out. They leave a measurable difference. If we didn't correct for these effects, your GPS location would drift by about 10 kilometers every day. After a week, it would be hopelessly wrong. After a month, you'd be navigating on a different planet. The only reason GPS works is because we adjust for the curvature of spacetime. That's how real Einstein's theory is. It isn't abstract. It isn't philosophical. It's part of the infrastructure of modern life. Every time your phone says, "You are here," spacetime is whispering the answer. Yet, even with this remarkable success, the deeper truth remains elusive. We know how spacetime behaves. We know how to calculate its curves, predict its ripples, measure its distortions. But we still don't know what it truly is. To see why that matters, imagine zooming in, closer and closer, to any point in spacetime. In Einstein's picture, the closer you look, the smoother it becomes. Like zooming into a perfectly polished surface, the bumps disappear, the imperfections fade, and everything becomes flat and continuous. That smoothness is what allows general relativity to work so beautifully. It assumes spacetime is a differentiable manifold, a seamless fabric. But quantum mechanics disagrees. In the quantum world, smoothness is an illusion. Energy comes in quanta. Spin comes in quanta. Light comes in quanta. Nothing is continuous. When you zoom into the very tiniest scales, far beyond what any microscope can see, you reach the Planck length, a distance so small it defies imagination.
0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000
Fluctuations explode. Fields jitter. Virtual particles pop in and out of existence. Space and time themselves start to vibrate in unpredictable ways. Some theories predict that spacetime becomes foamy or frothy, with tiny bubbles forming and collapsing in trillionths of a trillionth of a second. Others propose that the fabric may dissolve entirely into tiny bits of information. In this realm, Einstein's smooth spacetime cannot survive. But purely quantum descriptions fail too. Quantum mechanics expects a fixed background, a stage on which particles appear and interact. Relativity says the stage itself is dynamic. It bends, stretches, vibrates, warps. You can't place quantum particles on a fixed spacetime because spacetime is part of the drama. It's as if one theory describes the actors, and the other describes the stage, but no one knows how to write a play where both coexist. This conflict becomes impossible to ignore in extreme situations, places where quantum mechanics and general relativity must both operate simultaneously. Inside black holes, for example. Or at the beginning of the universe, when everything was compressed into a region smaller than a single atom. Or during violent phenomena like neutron-star collisions and the birth of gravitational waves. In everyday life, the conflict is invisible because the effects are tiny. But in those extreme regions, the two frameworks don't simply disagree, they explode into contradictions. Something is missing. Some deeper theory must exist, one that includes both relativity and quantum mechanics in a single picture. A unified description. A quantum theory of gravity. That dream has driven physicists for nearly a century. Einstein spent the last decades of his life searching for such a theory, but without the tools of modern physics. He didn't get far. Today, we have new ideas, string theory, loop quantum gravity, emergent spacetime models, but none of them are proven. None of them have experimental confirmation. But even without proof, the more we probe spacetime, the more hints we find that something extraordinary lies beneath it. For example, consider entanglement. In quantum mechanics, two particles can become linked, sharing a connection that persists no matter how far apart they move. Measuring one instantly reveals the state of the other, even if they are on opposite sides of the galaxy. Einstein called this spooky action at a distance, because it seemed to violate the idea that nothing travels faster than light. But what if spacetime itself emerges from networks of entanglement? Some physicists propose exactly that. They imagine space not as a pre-existing fabric, but as a web of quantum relationships. The geometry we experience, the distances, the curves, the shapes, might arise from patterns of entanglement. In this view, space is not fundamental. Space is built from information. Others propose that spacetime is holographic, that everything inside a region of space can be described by information encoded on a surface surrounding it. This idea was born from black hole physics, from the observation that the amount of information a black hole can store is proportional not to its volume, but to the area of its event horizon. It's as if reality itself is a kind of hologram, a 3D experience projected from a deeper, lower-dimensional structure. Even more radical proposals suggest that spacetime might emerge from quantum error-correcting codes, the same kind of mathematical structures used to keep digital data safe from corruption. In these models, geometry is the result of redundancy, stability, repetition. The universe, in a sense, protects itself from errors by weaving spacetime into existence. None of these ideas are proven. They might all be wrong. But they share something important: they treat spacetime not as a fundamental substance, but as a construct, something built from deeper processes. This marks a profound shift in how we think about reality. Einstein saw spacetime as the foundation. Modern physics increasingly sees it as the product. If that's true, if spacetime is built from something deeper, then the question we have been asking for more than 100 years may need to be reframed. Instead of asking, what is spacetime made of, we might need to ask, what creates spacetime? And if spacetime itself is emergent, what does that say about time? Is time truly flowing? Or does the flow emerge from something timeless? Sooner or later, we must confront these questions head-on. And that takes us to one of the strangest concepts Einstein ever introduced, one so misunderstood, so counterintuitive, that even today most people get it completely backward: the relativity of simultaneity. And once you understand that, everything else, time dilation, length contraction, the shape of the universe, begins to fall into place. Einstein's relativity of simultaneity is one of those ideas that seems harmless at first, like a small detail tucked inside a larger theory. But once you understand it, truly understand it, you realize it shatters one of our deepest assumptions about reality. It challenges something so fundamental, so intuitive, that almost everyone resists it the first time they hear it. The idea is simple: two events that appear simultaneous to one observer may not be simultaneous to another observer who is moving relative to the first. That's it. One sentence. But that sentence uncovers a truth so powerful that it rewrites the structure of time itself. To see why, imagine the following scene. You're standing in the middle of a train platform, and a long train is passing by. At the exact moment the center of the train lines up with where you're standing, two bolts of lightning strike, one at the front of the train, one at the back. Because you're standing still on the platform, and because the strikes are equally far from you, the light from both bolts reaches your eyes at exactly the same moment. You naturally conclude the strikes occurred simultaneously. But imagine someone sitting inside the train, exactly at its center. This person is moving forward with the train, closer toward the point where the front lightning bolt struck and farther away from the point where the back bolt struck. So, the light from the front strike reaches them first. They conclude that the front lightning strike happened before the back one. Both observers are correct. Neither is wrong. Neither is confused. Neither is misinterpreting anything. The universe simply does not define a unique, universal now. This is the key: there is no God's eye view of time where all events line up simultaneously. Simultaneity is relative. It depends on your state of motion. And once you accept that, something astonishing happens: the flow of time itself becomes part of your trajectory through spacetime. Every observer slices the universe into past, present, and future differently. Your now is not the same as someone else's now. Two people standing still relative to each other can agree on what's happening at the same moment. But the instant someone starts moving, that agreement breaks down. Their slice of time tilts. Their sense of simultaneity rotates in spacetime. And this isn't just philosophical, it's physical. It means that the sequence of events can change depending on how you move. It means that time is not absolute. Time is not universal. Time is not a constant background flow shared by all observers. Instead, time is woven together with space, forming a single structure where everyone takes their own path. This is why Einstein spoke of a block universe, not because time is frozen or predetermined, but because past, present, and future exist as part of the spacetime geometry. The flow is how our consciousness moves through the block, not something spacetime itself does. Once you internalize that, the consequences ripple across everything we know about reality. We begin to see why time dilates, why clocks moving fast run slowly, why gravity slows time down, why your head ages slightly faster than your feet due to Earth's gravitational field. These are not separate phenomena, they are all manifestations of the same fact: motion and gravity tilt your slice of time relative to someone else's. And this tilt becomes enormous in extreme environments. Near the event horizon of a black hole, time drastically slows. An observer far away might watch. You descend and appear to freeze, never quite crossing the horizon. Meanwhile, from your perspective, time for the outside universe speeds up. Stars might live and die in moments. The universe might continue evolving right before your eyes. This is not science fiction. This is a direct consequence of general relativity. When we put all these effects together, spacetime begins to seem less like a stage and more like a dynamic, ever-shifting landscape. And in that landscape, one of the most surprising features is curvature. Gravity, Einstein realized, is not a force, it's geometry. Mass and energy tell spacetime how to curve. Curvature tells objects how to move. And what looks like gravitational attraction is simply an object following the straightest possible path through curved spacetime. This idea sounds poetic, almost metaphorical. But it's mathematically precise. Every prediction Einstein made based on it has been tested. One of the most striking tests came from studying the orbit of Mercury. Mercury's orbit doesn't quite match what Newton's laws predict. It shifts over time, as though something is gently tugging it out of place. For centuries, astronomers tried to explain the anomaly with new planets or unseen masses. But Einstein's theory predicted the exact discrepancy, 43 arcseconds per century. When calculations matched observations perfectly, it was the first big sign that Einstein was right. Another test came in 1919, during a solar eclipse. Light from distant stars bent around the sun exactly as his equations predicted. That experiment transformed Einstein into the most famous scientist in the world. Headlines declared that Newton had been overturned and that a new vision of the cosmos had arrived. But even with all these successes, there were still mysteries lurking within Einstein's equations. Mysteries he knew existed but couldn't resolve. Mysteries that forced physicists to confront the limits of general relativity itself. One of the strangest of these mysteries involves an idea that seems innocent at first but grows increasingly unsettling the more you think about it. If gravity is geometry, then what happens when curvature becomes infinite? In other words, what does it actually mean when spacetime breaks? That is the essence of a singularity, the point where the equations describing spacetime stop working, where curvature becomes infinite, where the concept of space and time cease to exist in any normal sense. And these singularities aren't rare theoretical curiosities. They exist in black holes. They appear when we model the beginning of the universe. They show up whenever matter collapses too far. They are signs that our theories are incomplete. Yet, if singularities exist, they raise a troubling question: is the universe fundamentally knowable? Can we make predictions beyond these points? Can we meaningfully talk about what happens at the center of a black hole or before the Big Bang? Einstein's equations say no. They slam the door shut. They refuse to look deeper. But physicists do not like closed doors. And for decades, they have tried to pry this one open. This search leads us towards something profound, a realization that the ingredients of spacetime may include something unexpected. Quantum mechanics hints that spacetime might not be a smooth continuum but a fluctuating, probabilistic structure. Relativity insists on smoothness. The two perspectives appear incompatible. Yet, somewhere between them must lie the truth. And the next breakthrough in our story comes from a different concept altogether, one introduced by Einstein but misunderstood for generations. Gravitational waves. These waves will turn out to be the key to seeing spacetime not as something static, but something alive. Gravitational waves are one of those ideas that seem obvious in hindsight, almost like a natural consequence of Einstein's equations. But the truth is far stranger. For a long time, even Einstein wasn't sure they were real. He wrote about them, then doubted them. Then believed in them again. Physicists argued for decades over whether these waves were true physical phenomena or just mathematical artifacts, ripples on paper rather than ripples in reality. To understand why the debate lasted so long, imagine spacetime as a kind of fabric, not metaphorically, but literally, in the sense that it can stretch, twist, bend, and ripple. If a massive object accelerates, like two stars orbiting each other, or two black holes spiraling inward, it can create disturbances in that fabric that travel outward at the speed of light. These disturbances are gravitational waves. They aren't waves in a substance. They are spacetime changing shape. But the waves are incredibly faint. Even the collision of two black holes, each dozens of times more massive than the Sun, produces waves so subtle that by the time they arrive at Earth, they stretch space by less than the width of a proton over a distance of 4 kilometers. It's like detecting a change in the distance between two cities smaller than the diameter of a DNA molecule. That's why Einstein thought no one would ever observe them. They were too small, too delicate. But physicists are stubborn and patient and very good at building impossible machines. In the 1970s and 80s, a group of scientists began designing a device capable of detecting these almost imperceptible ripples. The idea grew into a project called LIGO, the Laser Interferometer Gravitational Wave Observatory. It used laser beams traveling down long, perpendicular tunnels to measure tiny shifts in distance, watching for the telltale stretching and shrinking of spacetime itself. For years, the machine heard nothing but noise. Billions of dollars, decades of effort, and not a single gravitational wave. Many doubted it would ever work. But on September 14, 2015, just days after LIGO's detectors were upgraded, something extraordinary happened. Deep in the data stream, just a subtle swoop. A delicate chirp was the signal of two black holes merging more than 1 billion light-years away. For the first time in human history, we weren't just looking at the universe. We were listening to it. The signal was unmistakable. It matched Einstein's predictions perfectly. The frequency, the amplitude, the shape of the waveform, every detail aligned with two black holes spiraling together, then colliding to form one larger black hole. The universe had spoken in a language Einstein predicted a century earlier. And with that single detection, gravitational waves transformed from abstract possibility into physical reality. Suddenly, we could observe things that had been invisible for all of history. We could witness collisions in the dark. We could study black holes not by the light they emit, because they emit none, but by the ripples they produce in spacetime. And this new form of observation revealed something profound: spacetime isn't static. It isn't a silent stage. It vibrates. It rings. It carries echoes of cosmic events across billions of years. Gravitational waves also reveal something else: spacetime itself has energy. This is not an obvious concept. Waves that travel through a medium usually carry energy through the medium, not of the medium. But gravitational waves aren't like water waves or sound waves. They don't need a substance to move through. They don't propagate in space, they propagate as space. If gravitational waves can carry energy, that implies spacetime is not merely geometry, it behaves like a physical entity. It can store energy. It can transfer energy. It can oscillate. But this raises a subtle and disturbing question: if spacetime can ripple, does it also have a granular structure? Does it have a limit to how smooth it can be? If you push it far enough, does it break? The best clues to that question come from the most extreme events the universe has ever produced: black hole mergers, neutron-star collisions, and the faint remnants of the Big Bang itself. Each gravitational wave we detect carries a story about the fabric of the cosmos. Some waves tell us about mass and motion. Some tell us about extreme curvature. But others, those from the earliest moments of the universe, might tell us about something deeper: the texture of spacetime itself. If spacetime has a fundamental granularity, a minimum possible scale, we might detect it as distortions or fuzziness in gravitational wave signals. So far, the waves we've observed are remarkably clean, more precise than our theories expected. Smooth. Elegant. Too smooth, perhaps. This leads some physicists to suspect we're missing something. Because if spacetime is perfectly smooth at every scale, Einstein might be right all the way down, but quantum mechanics would be wrong. If spacetime is granular, quantum mechanics wins, and Einstein must be modified. But what if spacetime is neither smooth nor grainy? What if it emerges from something else entirely? This question pushes us toward the modern frontier of physics, a frontier where ideas become more imaginative, more abstract, and more unsettling than anything Einstein himself ever proposed. Some theories suggest that spacetime emerges from entanglement, from networks of quantum relationships connecting particles in a vast web. Others propose that spacetime behaves like a fluid, with geometry emerging the way waves emerge on water. But one idea stands out among all the others, an idea that merges gravity, quantum mechanics, information theory, and thermodynamics into a single puzzle: the connection between spacetime and entropy. This connection leads to a remarkable conclusion: the shape of space may depend on information, and the flow of time may depend on entropy increasing. In this view, time exists because information spreads. The arrow of time emerges from the growth of entropy. And spacetime. Geometry may literally encode the history of information being rearranged. This is not speculation. It comes from one of the most solid and surprising results in physics: the laws of black hole thermodynamics. And that is where the next chapter of our story begins. The story of black hole thermodynamics begins with a simple question, one so natural, so obvious, that it seems almost ridiculous to ask. Do black holes have entropy? Entropy, in physics, is a measure of disorder. It counts how many microscopic arrangements correspond to the same macroscopic state. A gas in a box has high entropy because there are many ways to rearrange its molecules while keeping it looking the same overall. A perfectly ordered crystal has low entropy. The universe tends to evolve toward states of higher entropy, which is why time has a direction. It's why eggs break, why heat spreads, why memories form in one direction and not the other. Entropy is tied to information. If you know less about a system's precise arrangement, its entropy is higher. At first glance, black holes seem like the simplest objects in the universe. According to the famous no-hair theorem, a black hole is fully described by only three numbers: its mass, its charge, and its angular momentum. That's it. Everything else, every detail about what fell into it, is erased behind the event horizon. So if black holes erase information, do they violate the second law of thermodynamics? This was the puzzle that bothered physicist Jacob Bekenstein in the early 1970s. He argued that black holes must have entropy, because if they didn't, you could destroy entropy by throwing disordered matter into them, violating a fundamental law of nature. But if black holes have entropy, what determines it? What is it proportional to? Bekenstein proposed something radical. The entropy of a black hole is proportional not to its volume but to its surface area, the area of its event horizon. This idea was astonishing. In everyday physics, entropy is an extensive quantity, it scales with volume. But Bekenstein was suggesting that the deepest secrets of a black hole, the information it contains, are stored on its surface. This was the first crack in the door leading toward the holographic principle. But Bekenstein's argument had a problem. If black holes had entropy, they should also have temperature. And if they had temperature, they should radiate heat. But that contradicted everything relativity said about black holes. They were supposed to trap everything, including light. That paradox was resolved by Stephen Hawking in 1974, in one of the most brilliant and surprising calculations in the history of physics. Hawking showed that quantum effects near the event horizon cause black holes to emit radiation, now known as Hawking radiation. It isn't light escaping from inside the black hole, it's a quantum process occurring at the boundary. And the temperature of this radiation is inversely proportional to the mass of the black hole. The bigger the black hole, the colder it is. With one stroke, Hawking proved Bekenstein right. Black holes do have entropy. And the formula he derived for that entropy, known as the Bekenstein-Hawking entropy, is staggeringly elegant. The entropy of a black hole equals 1/4 of its event horizon's area, measured in Planck units. 1/4 of the area. Not the volume. Not the radius. The area. This result stunned physicists. It suggested something extraordinary. The fundamental degrees of freedom in gravity, the bits that encode the structure of spacetime, live not in the bulk but on surfaces. This is the holographic nature of gravity. A black hole contains an enormous amount of entropy, far more than any ordinary object of the same size. And because its entropy is tied to area, not volume, its event horizon behaves like a storage device for information. The implication is unavoidable. The true description of spacetime might live on lower-dimensional boundaries. This idea became the seed for the holographic principle, most famously expressed in the AD/CFT correspondence proposed by Juan Meldacena in 1997. In that framework, a gravitational universe in a higher dimensional space is exactly equivalent to a non-gravitational quantum theory living on its lower dimensional boundary. Gravity emerges from quantum physics without gravity. Spacetime emerges from information. Geometry emerges from entanglement. Suddenly, concepts that had seemed unrelated, entropy, quantum mechanics, spacetime curvature, were woven together into a coherent tapestry. And black holes, once thought to be the endpoints of physics, became laboratories for exploring the nature of reality itself. But the story doesn't end there. Because once Hawking radiation enters the picture, a new mystery emerges, one even deeper, even stranger, and even more troubling than the existence of entropy or the holographic nature of space. It is the black hole information paradox. This paradox is not a mere technical issue. It is a direct clash between the two greatest pillars of modern physics. It says that if black holes evaporate completely, as Hawking's calculation predicts, then the information about everything that fell into them is lost forever. But quantum mechanics forbids information loss. Something must give. Either quantum mechanics is wrong, unthinkable, given its precision. Or general relativity is wrong, expected, but still monumental. Or our understanding of spacetime is incomplete, and something deeper lies below. This paradox has pushed physicists to reimagine what the event horizon is, how information is stored, and whether spacetime itself might be built from quantum entanglement in a fundamentally holographic way. Some physicists propose that the event horizon is not a smooth surface but a firewall, a region of extreme quantum energy that destroys anything falling through. Others argue for soft hair, quantum degrees of freedom living on the horizon. Some suggest that information escapes in subtle correlations within Hawking radiation. Others propose that spacetime connects the inside and outside of black holes through tiny wormholes created by entanglement. Each idea is bold. Each idea is incomplete. But one assumption sits at the root of all of them, that spacetime, as Einstein imagined it, cannot be the full story. It cannot remain smooth and continuous down to the smallest scales. It must be built from something deeper. And the best clues come not from the largest structures in the universe but from the tiniest ones, from the Planck scale, where quantum gravity takes over. As we move toward those scales, the idea of spacetime begins to dissolve. Distances lose meaning. Time becomes uncertain. Geometry fluctuates wildly. The smooth fabric Einstein described turns chaotic, frothy, probabilistic. This is where our journey is heading next, to the edge of our understanding, where spacetime crumbles into quantum foam. As we descend toward the Planck scale, the unimaginably tiny realm where distances are a trillion times smaller than an atom, the familiar concepts of space and time begin to disintegrate. Einstein's smooth spacetime, with its elegant curvature and well-defined geometry, no longer makes sense in this domain. The very idea of a point in space becomes ambiguous. Distances blur. Time ceases to flow in any ordinary sense. This chaotic, turbulent landscape is often called quantum foam, a term introduced by physicist John Wheeler. Wheeler imagined spacetime at the smallest scales as a seething storm of fluctuations, tiny bubbles popping in and out of existence, miniature wormholes forming and collapsing, loops of geometry twisting and untwisting faster than any physical process we can imagine. But this image, vivid as it is, only hints at a deeper truth: spacetime may not be fundamental at all. General relativity tells us that spacetime is a geometric entity. Quantum mechanics tells us that everything fundamental must come in discrete units. These two ideas cannot coexist peacefully. Something must give. This tension is one of the biggest reasons physicists have searched for a quantum theory of gravity, a theory that can describe spacetime the same way quantum field theory describes particles and forces. One candidate is string theory, which proposes that the fundamental building blocks of the universe are not particles but tiny vibrating strings of energy. In string theory, spacetime is not given, it emerges. The geometry of the universe is determined by the ways strings vibrate, fold, and interact. The theory naturally includes gravity and avoids the infinities that plague quantum attempts to describe spacetime directly. But string theory operates in higher dimensions, 10 or 11 dimensions, depending on the formulation. These extra dimensions are curled up at the Planck scale, too small to detect directly. And while the theory is mathematically beautiful, it has yet to produce experimental predictions that can be tested. Another approach is loop quantum gravity, which attempts to quantize spacetime itself. Instead of treating spacetime as smooth, loop quantum gravity treats it as a network of tiny loops, discrete chunks of geometry. Areas and volumes become quantized. Spacetime becomes a lattice of finite, countable pieces. This approach avoids singularities. It predicts a finite minimum volume. But it, too, is incomplete. It does not incorporate all the forces of nature. It describes gravity well, but struggles to connect with particle physics. These frameworks, different as they are, point toward a common realization: the smooth spacetime we experience may be like the surface of water. It appears continuous, but underneath lies something granular, something dynamic, something deeper. And this deeper structure may not look anything like space or time. Increasingly, physicists suspect that entanglement, the quantum connection between particles, might be the true foundation. That space emerges from patterns of correlation. That distance arises from how strongly systems are entangled. That geometry is a manifestation of information. In this model, spacetime is like a story woven from relationships rather than objects. This idea gained enormous traction after discoveries involving the holographic principle. As physicists studied black holes through the lens of holography, they realized something remarkable: the equations describing spacetime curvature were equivalent to equations governing quantum entanglement on a boundary surface. This led to the astonishing proposal that entanglement builds spacetime. Imagine a network of qubits, a huge web of quantum information. If the qubits are strongly entangled, the geometry of space is smooth and connected. If entanglement is weak or absent, the geometry falls apart. Distances stretch. Wormholes collapse. Entire regions of spacetime can disconnect or vanish. In fact, certain calculations suggest that the interior of a black hole might be built from entanglement between the degrees of freedom inside and outside the horizon. Removing that entanglement destroys the interior, turning the black hole into something radically different. It's a shocking conclusion: the very shape of space may be held together by quantum entanglement. But if this is true, it leads to an even more profound idea, one that reshapes our understanding of time itself. Time appears to flow because entropy increases. This isn't just thermodynamics, it's a statement about information. As quantum information spreads, as entanglement grows, as systems evolve from order to disorder, time emerges as the direction in which information disperses. Time is not a fundamental parameter. It's a consequence of how information changes. This perspective helps resolve puzzles like the arrow of time, why the past is fixed and the future is open. It also explains why we remember the past but not the future. Information accumulates, but never unaccumulates. Entropy grows, but never shrinks globally. If both space and time emerge from deeper rules of information, then spacetime as a whole may be something like a large-scale illusion, a powerful and consistent one. But not fundamental. Yet there is still a problem. If spacetime is emergent, what happens in the most extreme environments, inside black holes, before the Big Bang, or at the Planck scale, where the emergent description breaks down? What existed before spacetime emerged? What does time mean when entropy is zero? What is geometry when entanglement hasn't yet formed? These questions point us toward the ultimate mystery, one that has haunted physicists from Einstein to Hawking to today's leading researchers. To understand this mystery, we must look at the origin of spacetime itself. The birth of the universe. Not just the Big Bang, but what may have come before it, and what it tells us about the true nature of the cosmos. That's where our story turns next. To understand the true nature of spacetime, we eventually reach a place where every theory, general relativity, quantum mechanics, holography, thermodynamics, information theory, collides. That place is the beginning of the universe. The Big Bang. For decades, the Big Bang was described as a kind of cosmic explosion, a singular moment when the universe burst into existence from an infinitely dense point. But that picture is misleading. The Big Bang was not an explosion in space, it was the origin of space itself. Space didn't exist before. Time didn't exist before. The universe didn't expand into something, it expanded into itself. Einstein's equations describe the evolution of spacetime from that moment onward. But the equations break down when you push them all the way to the beginning. They produce a singularity, an infinite curvature, an infinite density, a point where the mathematics collapses. Most physicists agree today that the classical Big Bang singularity is not real. It's a sign that general relativity is being pushed beyond its limits. Some deeper, quantum description is needed, a description where spacetime isn't assumed to be smooth and continuous. This is the same problem encountered at the center of a black hole. The equations predict a singularity not because one exists, but because the theory is incomplete. So what really happened at the beginning? One idea is that quantum gravity smooths out the singularity. In loop quantum cosmology, for example, the Big Bang is replaced by a bounce. Instead of emerging from nothing, the universe compresses to a minimum size and then rebounds. In this picture, a previous universe collapsed, and ours was born from the rebound. String theory suggests something different, that the Big Bang might be the collision of higher dimensional brains. Or that extra dimensions shrink and expand in cycles, producing repeating epochs of cosmic evolution. Other ideas propose that the universe emerged from a quantum fluctuation, or that spacetime itself nucleated from a more fundamental entity. Still others argue that the universe is eternal, and the Big Bang was simply a phase transition, a change in the state of spacetime. But regardless of the model, one truth emerges: the Big Bang marks the boundary of where classical spacetime makes sense. Beyond that, the idea of spacetime as a smooth continuum dissolves. There is no before in the usual sense, because before requires time, and time itself may have been born in that transition. This leads to a remarkable conclusion. Time may not be fundamental. It may have begun as a result of entropy increasing. In the earliest moments of the universe, everything was extraordinarily ordered, far more ordered than seems reasonable. It's almost disturbing how low the entropy of the early universe was. A tiny fraction of a second after the Big Bang, the universe was hot, dense, uniform, and smooth. That smoothness implies a very low entropy state. And from that point on, entropy has increased, creating the arrow of time and the flow of history. But why was the early universe so ordered? Why did it start in such a special, improbable state? This question goes beyond physics. It touches on cosmology, philosophy, and the foundations of existence. Some physicists argue that the universe simply started that way as a brute fact. Others believe that deeper laws enforce that order. Still others suspect that our universe is one region within a far larger multiverse, most of which is chaotic, but ours happens to be in a rare low-entropy bubble. In these models, time itself might be local. It might flow differently in different regions of the multiverse. Or it might not flow at all in the deepest layers of reality. But no matter the explanation, one fact remains: the early universe forces us to rethink what spacetime truly is. And that rethinking becomes even more dramatic when we consider cosmic inflation. Inflation is the idea that, in the tiniest fraction of a second after the Big Bang, the universe expanded exponentially, far faster than the speed of light. This doesn't violate relativity because it's space itself expanding, not objects moving through space. Inflation explains why the universe looks flat, why it's uniform, why distant regions share the same temperature despite never having been in contact. But inflation introduces a new mystery. If the universe expanded that quickly, what drove the expansion? What field, what energy, what mechanism was responsible? Some inflationary models predict an eternal process, space continually inflating in some regions while forming bubble universes in others. In this picture, our universe is just one bubble in a vast cosmic sea. Other bubbles might have different physical laws, different particles, different dimensions. And if that's true, spacetime as we know it is only a tiny piece of a vastly larger structure, one where geometry, time, and physics vary from place to place. The implications are overwhelming. But even inflation does not answer the most fundamental question. What is spacetime made of? Is it geometry? Is it quantum information? Is it a hologram? Is it emergent from something even deeper? As physicists explored these questions, they discovered something astonishing, something that ties together black holes, entropy, entanglement, and the birth of the universe. It's a principle so profound that many consider it one of the deepest insights in all of theoretical physics. The principle is this: spacetime is not a backdrop. It is a consequence. It is what happens when quantum information arranges itself in a particular way. To understand how this works, we need to explore an idea that might be the most beautiful insight ever proposed about the structure of spacetime, an idea that says geometry itself arises from entanglement patterns, and that the gravitational force is simply the way information pulls itself into shape. This idea has a name, and it begins with the realization that spacetime behaves like a thermodynamic system. The idea that spacetime behaves like a thermodynamic system is one of the most surprising, most elegant, and most far-reaching insights in modern physics. It suggests that gravity, the force shaping galaxies and orchestrating the cosmic ballet of planets and stars, might not be fundamental at all. Instead, it might be a statistical effect, like temperature, like pressure, like entropy, a large-scale phenomenon emerging from the collective behavior of microscopic constituents. To see how this idea arises, we return once more to black holes. When Jacob Bekenstein argued that black holes have entropy, and Stephen Hawking showed they have temperature, physicists were stunned. Black holes, the simplest and most enigmatic objects in the universe, obey the same thermodynamic laws as steam engines and refrigerators. Their entropy grows. Their temperature changes with energy. They satisfy analogues of the laws of thermodynamics. But this wasn't just an analogy, it was a clue. If black holes obey thermodynamics, then spacetime itself must have microscopic degrees of freedom, hidden components that we cannot directly see. But whose collective behavior gives rise to the smooth geometry Einstein described? This realization led physicist Ted Jacobson to a revolutionary insight in 1995. He discovered that Einstein's field equations, the core equations of general relativity, can be derived from the simple statement that entropy is proportional to area, and heat flows across horizons. In other words, gravity is a consequence of thermodynamics. Imagine that. Einstein spent years discovering the equations of general relativity by thinking deeply about geometry and acceleration and the nature of gravity. But Jacobson showed that if you assume spacetime has entropy and temperature, Einstein's equation emerges automatically. Geometry becomes a thermodynamic equation of state. Gravity becomes emergent. This idea was pushed further by physicist Eric Verland, who proposed that gravity is not a force at all, but an entropic phenomenon. When information rearranges itself, when entropy increases, matter feels a pull that we experience as gravity. That pull is simply the universe trying to maximize entropy. This perspective changes everything. It suggests that spacetime curvature is the thermodynamic response of a deeper informational structure. That geometry is nothing more than a coarse-grained description of microscopic variables. That the laws of gravity reflect the statistical behavior of something else, something not geometric, not continuous, not classical. This brings us full circle to the idea that spacetime might be built from entanglement. One of the key insights supporting this idea comes from studies of the Ryu-Takayanagi formula, discovered within the holographic framework. The formula provides a remarkable bridge between geometry and quantum information. It states that the amount of entanglement between regions of a quantum system corresponds exactly to the area of a minimal surface in the gravitational dual. Let that sink in. A purely quantum concept, entanglement entropy, corresponds to a geometric quantity, area, in a gravitational universe. The shape of spacetime is literally determined by entanglement. If entanglement decreases, spacetime constricts. If entanglement increases, spacetime expands. If entanglement is severed entirely, spacetime tears apart. This idea has profound Implications. It means that geometry is woven from interactions between quantum systems. It means that without entanglement, there is no space. And it suggests that wormholes, bridges connecting distant regions of spacetime, may correspond to entangled pairs of particles. ER equals EPR, proposed by Leonard Susskind and Juan Meldacena, encapsulates this in a single equation. ER refers to Einstein-Rosen bridges, wormholes. EPR refers to Einstein-Podolsky-Rosen pairs, entangled particles. The conjecture suggests that entanglement and spacetime connectivity may be two sides of the same coin. If two particles are entangled, perhaps they are connected by a tiny wormhole in spacetime. Not a wormhole we could travel through, not a science fiction portal, but a geometric reflection of their quantum connection. And if this applies to two particles, could the entire structure of spacetime be one giant network of such connections? Many physicists believe so. In this picture, the universe is a vast web of quantum entanglement. Spacetime is the large-scale pattern that emerges from the intricate weaving of that web. Gravity is the way information arranges itself. Black holes are the densest tangle of entanglement possible. And singularities are simply places where the emergent description fails. But this leads to a deeper question, one that is almost unnerving. If spacetime emerges from quantum information, where do the laws governing that information come from? Are they fundamental? Do they emerge from something deeper? Is there a level below entanglement, something even more basic? Some theories suggest that the universe might not be a geometric object at all, but a computational one. That the evolution of the cosmos is, at its heart, a process of computation, quantum information being updated, processed, rearranged. In this view, the laws of physics are algorithms. Spacetime is the output. Others propose that the universe is a kind of code, an error-correcting code, no less. In these models, the stability of spacetime, the resilience of geometry, the smoothness of gravitational interactions, all arise because the underlying quantum code protects information from being lost. If that is true, then the universe is fundamentally digital in some sense, while appearing analog at large scales. But beneath all these ideas lurks a deeper mystery, one that none of our current theories fully resolve. If spacetime emerges from something else, can it ever be destroyed? What happens when entanglement patterns shift, collapse, or change? What happens at the edges of spacetime? What happens inside black holes? What happens at the beginning and end of the universe? These questions push us toward the most speculative, yet most profound frontier in modern physics, the possibility that spacetime is not unique, not fixed, not complete. That spacetime itself can be created, destroyed, rearranged, perhaps even manufactured in a laboratory under the right conditions. And if that's true, then the universe may be far stranger than anything Einstein ever imagined. The idea that spacetime can be created, or even engineered, is not science fiction anymore. It emerges naturally from the notion that spacetime is not fundamental but emergent. If geometry is built from quantum entanglement, then, in principle, changing entanglement could create new regions of spacetime or modify existing ones. This is the kind of possibility that would have seemed absurd a century ago, but today, it is taken seriously by some of the world's leading physicists. To understand why, we must return to something simple yet powerful: entanglement is not static. It evolves. It spreads. It reorganizes itself. And this rearrangement is what shapes the structure of spacetime. In many quantum systems, entanglement behaves like a fluid, it flows through the system, redistributing correlations. In condensed matter physics, for example, the amount of entanglement determines whether a material behaves like a conductor, an insulator, or a superfluid. In high-energy physics, Entanglement controls how information is distributed among fields. If spacetime itself emerges from entanglement, then this flow of information determines how geometry changes. This is precisely what happens in black holes. When matter falls into a black hole, the horizon grows. The area increases. The entropy rises. This is not because the horizon physically swallows matter like a mouth, it is because new quantum degrees of freedom become entangled with the black hole's internal states. The growth of the horizon is the geometric reflection of increasing entanglement. In a strange and beautiful way, black holes teach us that spacetime responds to information. That geometry rearranges itself when information enters or leaves a system. And this same principle applies at the cosmic scale. Consider the expansion of the universe. As space grows, entropy increases. As entropy increases, the arrow of time becomes stronger. As time flows, entanglement spreads. And the geometry of the cosmos unfolds. The evolution of the universe is a kind of cosmic computation, where each step is encoded in the changing structure of spacetime. But this raises a subtle problem. If spacetime emerges from entanglement, what determines the rules of entanglement? What governs the network itself? What is the substrate beneath the quantum world? Some theorists suspect that the universe is built from something more fundamental than quantum mechanics, something deeper than wave functions and uncertainty principles. Perhaps the underlying layer is discrete, like bits in a computer. Or maybe it is continuous, but not geometric, more like a field of pure relationships, where the only thing that exists is the connections between abstract states. Others propose that the universe arises from a principle of extremization, an optimization process that selects the most stable, most coherent informational configuration. In such a view, spacetime is the result of the universe finding the simplest way to encode its own dynamics. There are even proposals that the universe is fundamentally logical, a structure built from propositions, proofs, and computational rules, where physical reality emerges as a necessary consequence of mathematical consistency. In this picture, spacetime is not a thing, it is a property of a deeper logical system. These ideas may sound abstract, but they help make sense of phenomena that classical physics struggles to explain, such as the behavior of quantum fields in curved spacetime, the nature of singularities, and the origin of the laws of physics themselves. Yet, even as these theories push into the deepest foundations of reality, they all face the same challenge. How do we test them? The Planck scale, where spacetime's fabric breaks down, is so tiny that no experiment can directly probe it with current technology. The energy required to examine distances that small is far beyond anything humanity can generate. And so, physicists must rely on indirect evidence, subtle deviations from predictions, faint imprints left in the cosmic microwave background, mathematical consistency, and clues from black hole physics. One of the most promising sources of such clues is the early universe itself. In the earliest instance after the Big Bang, the universe was so hot and dense that quantum gravity effects should have been significant. If we could decode the patterns in the cosmic microwave background, the faint afterglow of the Big Bang, we might find signatures of quantum spacetime. Tiny fluctuations, patterns of polarization, variations in temperature, these may all carry imprints of the quantum processes that preceded the classical universe. But the data is noisy. The signals are faint. And no definitive signature of quantum gravity has yet been found. Still, physicists keep searching. Because unless we can connect these ideas to observations, they remain elegant speculation. Another place to look for clues is black hole evaporation. If information is truly preserved in Hawking radiation, then the radiation must contain subtle correlations encoding the details of everything that fell in. Detecting those correlations is far beyond our current abilities, but future technologies, perhaps involving quantum sensors or gravitational wave observatories, might provide a path forward. And then there is the possibility that spacetime can be simulated. If spacetime is emergent, and if the mechanism of its emergence is understood, then in principle, one could reproduce spacetime in a quantum system. A quantum computer, for example, might simulate entanglement patterns that recreate gravitational behavior. This would be a kind of laboratory spacetime, an artificial geometry built from qubits. While still a distant goal, small steps in that direction have already been taken. Physicists have used quantum simulators to model aspects of black hole dynamics, wormhole-like behavior, and holographic dualities. These experiments are rudimentary, but they hint at a profound possibility that the universe might be understandable not only theoretically but constructively. That we might one day build miniature universes, not in the science fiction sense, but in the quantum sense, by arranging information in the right way. If that is true, then our understanding of spacetime would shift from passive observation to active creation. We wouldn't simply describe the fabric of reality, we would be able to generate it. This possibility leads to a deeper and more philosophical question. If spacetime can be created, then what is the role of observers? Are we part of the process that gives rise to spacetime? Does consciousness affect the emergence of geometry? Or is observation simply another form of information exchange? Some physicists avoid these questions. Others confront them directly. But one thing is certain, the more we learn about spacetime, the stranger it becomes. The simple picture Einstein gave us, a smooth, continuous fabric, was revolutionary for its time. But modern physics reveals something far more intricate, far more dynamic, far more interconnected. Spacetime is not a stage. It is a network of relationships. It is an expression of quantum information. It is the geometry of entanglement. It is an emergent phenomenon. And if all this is true, we must now ask the most profound question of all. What sits beneath spacetime? What is the ultimate foundation of reality? That question is where our story now leads. To search for what lies beneath spacetime is to stand at the edge of human knowledge. It is like sailing toward the horizon, knowing that every step carries you farther from what is familiar and deeper into territory where even our best concepts begin to fail. And yet, this is exactly where modern physics points us, toward a realm where our everyday intuitions about space, time, causality, and even existence itself are stripped away. One of the first hints comes from the fact that spacetime may not be unique. In general relativity, the geometry of spacetime is determined by mass and energy. But if spacetime is emergent, then perhaps different microscopic structures could produce different macroscopic geometries, different versions of spacetime. In this sense, our universe's spacetime might be just one of many possible emergent fabrics, each arising from a distinct underlying structure. Imagine different kinds of crystals. Each crystal lattice produces its own macroscopic properties: hardness, transparency, conductivity. Yet these differences come entirely from the way atoms are arranged. Similarly, spacetime might be one phase of a deeper informational substrate, a particular arrangement of quantum degrees of freedom. Different arrangements could produce different laws of physics. This idea is dizzying, but it also aligns with the possibility of a multiverse. If the universe can exist in different phases, then regions of spacetime might crystallize into different laws, different constants, different dimensions. But even if there are many possible spacetimes, that still leaves the question: what is the substrate? Is it quantum fields? Is it entanglement networks? Is it information itself? Or something stranger? Some physicists propose that reality might be fundamentally algebraic. That the basic ingredients of the universe are not particles or fields, but mathematical relations, abstract operators whose interactions give rise to observable physics. In this picture, spacetime emerges from the structure of the equations. themselves, not from anything physical. Others look at category theory, a branch of mathematics dealing with relationships and transformations rather than objects. According to this view, spacetime is not a thing, it is a pattern of interactions. Reality is made not from entities but from processes. Then there is the idea that the universe is fundamentally computational, that its evolution is a sequence of operations acting on bits or qubits. This doesn't mean the universe is a literal computer built by some external programmer. Rather, the rules of physics might simply be the rules of information processing. Spacetime would be a macroscopic illusion generated by the flow of computation beneath it. Stephen Wolfram and others have proposed that networks, hypergraphs, with simple update rules, might produce emergent structures resembling spacetime. Quantum graphite models suggest something similar, nodes and links rearrange themselves, forming geometric patterns as the system cools. In these models, spacetime is like a crystal emerging from a molten sea of information. But perhaps the most intriguing idea is that spacetime emerges from quantum entanglement through something called tensor networks. In these networks, each node represents a quantum state, and the links represent entanglement. By arranging them in particular patterns, like a web of interconnected quantum systems, you can produce geometries that look astonishingly like real spacetime. Distances, curvature, and even gravitational dynamics arise naturally from the structure of the network. This idea is beautifully simple. Space is what entanglement looks like when you zoom out. This perspective offers a radically new interpretation of Einstein's equations. Instead of describing geometry directly, they become equations governing how entanglement spreads across the network. Gravity is not a fundamental force, it is the system adjusting its entanglement to maintain consistency. But this leads to an even deeper question. What determines the pattern of entanglement? Is it imposed by some deeper law? Does it arise spontaneously? Was it set at the beginning of the universe? Or is it continuously updated as the universe evolves? At this point, physics approaches the limits of current knowledge. We can describe how spacetime behaves. We can describe how it might emerge. But we cannot yet describe what makes it emerge in the first place. And then there is the strangest possibility of all, that spacetime, matter, gravity, and quantum mechanics are not separate things. That they are all aspects of a single underlying structure. A structure that is not spatial, not temporal, not quantum in the usual sense. Something prior to spacetime. Something prior to particles. Something prior to entanglement. Physicists call this pre-geometry. Pre-geometry is not a specific theory, it is a category of possibilities. It represents the idea that the universe has a foundation that is not geometric, not physical, not even necessarily mathematical in the way we normally think. It is pure structure, pure process, pure relation. And from that foundation, everything emerges: time, space, matter, energy, quantum fields, atoms, galaxies, consciousness, history. Everything. This is a remarkable idea, but also a humbling one. Because it means we may never be able to fully visualize or comprehend the true foundation. Our brains evolved to navigate 3 dimensions of space and 1 dimension of time, not to grasp hyperabstract structures with no geometry. Yet even if the underlying reality is beyond our intuition, we are beginning to see its fingerprints. They appear in black hole thermodynamics, in holography, in entanglement entropy, in gravitational waves, in quantum fields, in the cosmic microwave background, in the very emergence of time. Spacetime is not fundamental. It is a consequence. It is a clever, elegant approximation that our universe uses at large scales. But beneath spacetime, something else lurks. Something deeper. Something that binds together every idea we've explored. Something that explains why the universe behaves the way it does. And if we want to understand that something, we must now confront the most mysterious part of all, the nature of time itself. Because while space might be emergent, time is even more elusive. And understanding time is the key to understanding reality. If space is elusive, time is downright haunting. We feel it constantly, it shapes every experience, every memory, every expectation we have. Yet when physicists try to pin down what time is, it slips through their fingers like smoke. In everyday life, time feels simple, it flows. It moves forward. The past is fixed, the future is open, and we ride the current from one moment to the next. But the more deeply we look, the more this intuition dissolves. Einstein shattered the idea of a universal present. The relativity of simultaneity destroyed the notion that all observers experience the same now. Time became local, personal, intertwined with motion and gravity. A clock on a mountain ticks faster than a clock at sea level. A fast-moving particle lives longer. A black hole stretches time until it freezes at the horizon. So whose time is real? Relativity refuses to choose. It treats time as another dimension woven into spacetime. In Einstein's block universe, all moments, past, present, and future, exist together. The flow of time is not something in the equations, it is something in our perception. But this view clashes with our experience. It clashes with thermodynamics. And it clashes with quantum mechanics, which evolved systems in time using a fundamental parameter that behaves nothing like Einstein's time. This contradiction hints at something crucial. Time might not be fundamental. Entropy gives us a clue. The arrow of time, the reason we can't remember the future, comes from the fact that entropy increases. If the universe began in an incredibly low entropy state, then every moment afterward naturally moves toward higher disorder. And that movement is what creates the sense of time flowing. In this view, time exists because the universe started ordered and is becoming less ordered. It's shocking to think that time, the most basic thing we feel, might be a side effect of the universe's initial conditions. If the early universe had been high in entropy, time might not flow at all. Events would not unfold, memories would not form, history would not exist. Some physicists argue that time might be nothing more than a convenient bookkeeping device. A parameter that helps us keep track of how quantum states change. But the states themselves might not care about time at the deepest level. In the Wheeler-DeWitt equation, a key equation attempting to unify quantum mechanics and gravity, time simply disappears. It's not there. The universe is static. How do we reconcile this with our experience? One proposal is that time emerges from entanglement. When one part of the universe becomes entangled with another, you can track the growth of correlations, and this growth looks like the passage of time. In this picture, time is a measure of how entanglement spreads. As the universe increases its web of correlations, time unfolds. Another perspective comes from the thermal time hypothesis, which proposes that time is not fundamental but emerges from the state of the universe. When a system has a certain statistical distribution of energy, this structure defines what we perceive as time. Different states correspond to different flows of time. This leads to a mind-bending idea: in regions with different entanglement or energy distributions, time might flow differently, not because of gravity or motion, but because the underlying quantum state is different. But what does it mean for time to emerge? How can something as central as time be an illusion? One analogy is temperature. A single molecule does not have a temperature. Temperature is a collective property that emerges only when many molecules interact. Similarly, time might not exist for isolated quantum systems. Only when enough degrees of freedom interact does something like a temporal flow arise. This is why time is so slippery. It's not built into the universe, it is built from the universe. This perspective helps resolve another long-standing puzzle, why quantum mechanics seems to require a fixed background time, but general relativity treats time as part of the geometry. If time is emergent, then quantum time and relativistic time are two approximations of the same deeper process. They both arise from the information content of the universe, but in different contexts. Another deep insight comes from the study of complexity. In holographic dualities, the growth of spacetime, especially in black holes, is associated with the growth of quantum complexity. The number of operations needed to describe a quantum state. As complexity increases, the interior of a black hole expands. The growth of space is tied to the growth of complexity. If complexity did not grow, time inside the black hole would freeze. This suggests a bold possibility: the flow of time is simply the growth of quantum complexity. As states become more complex, time moves forward. This elegantly ties physics, computation, and geometry together. The universe evolves because its underlying quantum state becomes more complex. Time is the measure of that evolution. Yet this raises an even more unsettling question: can time stop? If complexity reached a maximum, if the universe became maximally scrambled, would time cease to flow? Would the future simply vanish, not in a catastrophic sense, but in a structural one? Would the cosmos become timeless again, as it may have been before the Big Bang? We don't know. No theory has yet answered this fully. But what we do know is this: time is not what we think. It is not absolute. It is not fundamental. It is not a river flowing independently of the world. It is a feature that emerges from the universe's internal relationships. If time emerges, then so does causality, our sense of cause and effect. Even that, the backbone of physical intuition, might be a large-scale illusion. A pattern arising from deeper rules. This realization brings us face to face with a profound truth: the deeper we look, the less reality resembles the world we experience. The universe is not built from particles moving through a stage. It is built from information, entanglement, and relationships. Spacetime is a tapestry woven from these threads. Time is the unfolding of that tapestry. But if spacetime and time both emerge, then what does it even mean to ask what lies beneath them? What is the universe made of? What is the substrate that supports information itself? What is the thing from which physics emerges? To answer that, we must push beyond physics as we know it, into a realm where the lines between mathematics, computation, and ontology blur. And that is where our journey goes next. To ask what lies beneath spacetime is to challenge the very foundations of physics. It forces us to confront questions that are not just difficult, they are almost alien to the way our minds work. We are creatures evolved to navigate a world of objects, distances, and durations. But the deeper layers of the universe may not contain any of these familiar notions. They may not contain where, or when, or before, or after. Instead, they might be built from principles that are more abstract, more primitive, and more fundamental than anything in our everyday experience. One way to approach this question is to examine why spacetime appears so smooth and continuous. In Einstein's equations, spacetime behaves like a differentiable manifold, a structure where you can draw lines, measure distances, and talk about curvature. But if spacetime is emergent, this smoothness might be similar to how a fluid appears smooth, even though it is made from discrete molecules. The same could hold for spacetime. At the smallest scales, it may not be smooth at all. It may be granular, pixelated, or network-like. Loop quantum gravity is one attempt to capture this discreteness. In that framework, the fabric of spacetime consists of tiny loops woven into networks called spin networks. These networks define areas, volumes, and other geometric Quantities. Space becomes quantized, like the energy levels of an atom. But loop quantum gravity, while elegant, is only one possible picture. Other models propose that spacetime is built from graphs, simplicial complexes, quantum circuits, or algebraic structures. In every case, geometry arises not from continuity, but from the relationships between fundamental elements. This idea, that reality is relational, appears again and again. It suggests that nothing exists by itself. Everything exists only through its connections, through the information it shares or exchanges. Spacetime becomes the geometry of these relationships, not a fundamental backdrop. This relational view aligns beautifully with quantum mechanics, where particles do not have definite properties until they interact. It aligns with entanglement, where systems become inseparable at a fundamental level. It aligns with holography, where the inside of a region is determined by information stored on its boundary. The deeper physics goes, the more it insists on the primacy of relationships over objects. But the question remains, what kind of relationships? Some physicists suspect that the universe is built from pure information, the same way a computer program is built from bits. But unlike classical bits, quantum bits, qubits, can exist in superpositions and entangled states. If spacetime comes from entanglement, then perhaps the universe is a vast quantum computation unfolding according to simple rules. But who or what executes these rules? That question misunderstands the point. In this view, there is no external processor. The universe is the computation. Its evolution is the operation. Others suggest that logic is fundamental, propositions, implications, and transformations that form the basis of all mathematical structures. In such a picture, the laws of physics arise from the universe satisfying certain logical constraints. Geometry emerges because it is the most efficient way to encode relationships. Then there is a perspective drawn from category theory, that the universe is built from transformations rather than things. Objects are not fundamental, the processes between them are. Space and time are abstractions describing how these processes relate. Yet even these viewpoints, as radical as they sound, might not reach the bottom. One of the deepest clues about the substrate comes from black hole information. If black holes preserve information, and if that information is encoded in the geometry of spacetime, then information must be more fundamental than geometry. It must persist even when geometry collapses or transforms. This implies that the information network underlying the universe is more stable, more primitive, and more essential than spacetime itself. But another clue comes from the Big Bang. At the earliest moments, before the first fractions of a second, the universe was not big enough or stable enough to support spacetime as we know it. In that epoch, information existed without geometry. Quantum fields existed without classical time. Entanglement existed without a defined spatial layout. This suggests something remarkable: the universe had structure before it had spacetime. So what was that structure? One possibility is that the universe began as a dense, highly entangled state, a proto-universe, where correlations existed but were not arranged in space. As these correlations reorganized themselves, geometry emerged. Dimensions crystallized. Time unfolded. The universe expanded not into space, but into structure. This idea reframes the Big Bang not as an explosion in space but as a transition from a pre-geometric state to a geometric one, a phase change in the deep informational fabric. But even this view is incomplete, because it leaves unanswered a more profound question: why does the universe have any structure at all? Why does something exist instead of nothing? Why are there rules, patterns, relationships? Some scientists turn to mathematical universes, suggesting reality exists because mathematics is self-consistent. Others turn to quantum cosmology, proposing that the universe arises from a fluctuation in a larger metastate, a quantum ocean of possibilities. Still others appeal to symmetry principles, holographic constraints, or the dynamics of complexity. Yet all of these explanations share a common thread: they rely on structure that exists prior to spacetime. This leads us to a startling conclusion: spacetime is not the foundation of the universe. It is a consequence of something deeper, something that may not resemble anything we can visualize. The great challenge now is to decipher this hidden layer. To understand the rules that give rise to geometry, time, matter, and the laws of physics. To uncover the engine behind reality. And to make progress, physicists are beginning to explore ideas that blur the boundary between physics and computation, between mathematics and ontology, between what exists and what emerges. The frontier ahead is not just scientific, it is philosophical. And to continue our journey, we must confront questions that lie at the intersection of physics and meaning. Because once spacetime is no longer fundamental, we must face the final, unsettling question. If reality emerges from something deeper, then what is reality? To ask, what is reality, is to touch the oldest question in philosophy and the newest question in physics. For centuries, reality seemed obvious: it was the stuff around us, the matter we could touch, the space we could move through, the time we could measure. But the scientific revolution chipped away at this certainty. First came atoms, then fields, then spacetime, then quantum mechanics, and now something even stranger: the possibility that everything we experience is the emergent shadow of a deeper, hidden structure. What does it mean for reality to emerge? It means that the world we see, the world we think of as solid and objective, is only a high-level description, like the image on a screen that hides the complex circuitry beneath. Our senses evolved to interpret certain patterns, not to reveal the fundamental nature of the universe. And now, physics seems to be telling us that the fundamental layer is far beyond anything evolution prepared us for. This raises a profound question: if our experiences are emergent, is anything we perceive truly fundamental? Quantum mechanics already suggests that what we call objects are not solid things but excitations of fields, smeared out, probabilistic, defined only through interactions. Relativity tells us that space and time are intertwined, flexible, and mutable. Thermodynamics links the flow of time to entropy. Holography tells us that the universe might be encoded on a distant boundary. And the study of entanglement implies that space itself arises from correlations. If you strip all of this away, space, time, matter, fields, what remains? One answer is information. Not information in the everyday sense, but in the fundamental sense: patterns of distinctions, correlations, possibilities. Some physicists argue that the universe is not made of stuff, it is made of differences. The difference between one state and another. The way one quantum variable relates to another. In this view, reality is a network of informational relationships, and everything we see is a manifestation of those relationships taking shape. But information cannot exist by itself. It must be encoded in something. So what is the substrate of this information? What carries it? What stuff, if any, lies beneath? Here, physics begins to blur into mathematics. Some thinkers propose that the universe is a mathematical structure. Not that it obeys mathematical laws, but that it is mathematics, an abstract object whose structure gives rise to everything we observe. If this is true, then physical existence is simply mathematical consistency playing itself out. Others argue that computation, rather than mathematics, is fundamental. The universe evolves because it computes. Physical laws are programs. States evolve by simple rules iterated across vast scales. But this idea raises new questions: who or what runs the computation? If the universe is a computer, is it computing something beyond itself? Or is the computation self-sustaining, an intrinsic process with no need for an external interpreter? Then there is the possibility that reality is fundamentally relational, not built from things, but from interactions. In this view, what exists are not entities but processes, events where information is exchanged. Space and time emerge from the web of these events, and matter is simply the stabilization of certain patterns within this web. In all these perspectives, one theme repeats: nothing exists in isolation. Reality is not a collection of objects, it is a tapestry of relationships. But these relationships, no matter how fundamental, have an origin story. They must have emerged from something. This leads us to the most unsettling idea: reality may not have a single underlying layer. There may be no final substrate. Instead, reality could be a hierarchy of emergent layers, each giving rise to the next. Spacetime emerges from entanglement. Entanglement emerges from deeper structures. Those structures emerge from rules we don't yet understand. And those rules might arise from even more primitive principles. This infinite regress is uncomfortable, but it might reflect the true nature of existence. Reality could be like an onion with no core, each layer meaningful only in context of the one above and below it. Or it could be cyclical, emergence feeding back into itself. There is also the possibility that the foundation of reality is not a thing or structure, but a principle. Something simple, yet profound, from which everything else flows. A principle like symmetry, information conservation, or the optimization of complexity. Perhaps the universe exists because it is the simplest non-trivial system that can exist. Or the most efficient. Or the only self-consistent one. This brings us back to Einstein's legacy. He sought laws that were beautiful, universal, and logical. But what if the universe is not governed by laws in the way he imagined? What if the laws themselves are emergent? What if they are the statistical consequences of deeper processes? Some physicists speculate that the laws of physics might be like the laws of biology, not absolute, but evolved. The universe could be one of many possible systems, and the laws we observe might be those that allow stable structures, long-term complexity, and observers like us. This is not to say the universe is alive in any literal sense. But it might behave like a self-organizing system, adapting, optimizing, finding stable configurations in a sea of cosmic possibilities. If spacetime, matter, and even physical laws are emergent, then the ultimate question becomes: what is the universe trying to do? What is it organizing itself toward? What is the driving principle behind emergence? One candidate is complexity. Complex structures, from atoms to galaxies to life, arise naturally under the laws of physics. But perhaps the laws of physics themselves arose to support complexity. Perhaps the universe grows more complex because complexity is the natural consequence of its underlying rules. Another candidate is information. The universe might be maximizing the storage, distribution, or processing of information. Black holes, stars, crystals, and biological systems all organize information in different ways. Spacetime itself stores information in its geometry. A third possibility is that the universe is fundamentally about relationships, how things connect, correlate, and influence one another. Everything emerges from these connections. As strange as these ideas are, they all point to one conclusion: reality is far more subtle, layered, and dynamic than we ever imagined. We began with Einstein's spacetime, a smooth, geometric fabric. We peeled back that fabric to reveal quantum fields, entanglement, holography, and computation. And now we stand on the edge of a deeper mystery. If reality emerges from something more fundamental, then understanding that something may require new physics, new mathematics, new intuition, perhaps even new kinds of minds, Because the next step in this journey is to confront the deepest question of all. If the universe is emergent, then why does it give rise to observers like us? To answer that, we must explore the role of consciousness in a universe where spacetime is not fundamental. The emergence of observers, of conscious beings capable of questioning their own existence, is one of the most puzzling features of the universe. If spacetime, matter, and physical laws are all emergent, then consciousness must also arise from this layered structure. Yet consciousness feels different from other emergent phenomena. It is not merely a pattern in matter. It is the experience of being a pattern. The universe, through us, becomes aware of itself. Some scientists consider consciousness an unavoidable consequence of complexity. When information is processed in sufficiently intricate and integrated ways, subjective experience arises. But this explanation only pushes the mystery back a step. Why should integrated information produce experience? Why should matter at any level give rise to something so radically different from matter? Others propose that consciousness is not emergent at all, that it is fundamental. That awareness is a basic component of reality, woven into the universe at the deepest level. Not in a mystical sense, but as a primitive ingredient, like energy or information. In this view, consciousness does not arise from spacetime, spacetime arises from consciousness. This idea, known as panpsychism or integrated information theory's more radical interpretations, challenges the conventional hierarchy of emergence. But even if consciousness is not fundamental, its relationship to physical reality remains profound. Our perception of time, for instance, is intimately tied to consciousness. Time seems to flow, because our minds stitch together moments into a coherent narrative. Without consciousness, the block universe of relativity would simply exist, static, complete, unmoving. Consciousness imposes a sense of direction, of becoming, of change. This suggests that the flow of time may be a feature of observers, not of the universe itself. But if consciousness depends on the emergent structure of spacetime, and spacetime depends on entanglement, then consciousness is ultimately rooted in the deep quantum structure of reality. Our thoughts, our memories, our awareness, they are patterns within patterns, built from relationships that extend far beyond the brain. Some physicists speculate that consciousness might be linked to quantum processes. Not in the simplistic, pseudoscientific sense sometimes popularized, but in a more subtle way, the brain might exploit quantum coherence, entanglement, or complexity to perform computations that classical systems cannot. If this is true, then consciousness could be intertwined with the same principles that give rise to spacetime. But even this idea remains speculative. The truth is, no one knows exactly how consciousness arises. What we do know is that consciousness is inseparable from information. Our thoughts are arrangements of information. Our memories are stored information. Our perceptions are interpretations of information. And if the universe is built from information, then consciousness is a natural expression of its deepest layer. This perspective has a startling implication. Consciousness may not be something added to the universe, it may be something the universe inevitably produces. The same way certain chemical reactions inevitably produce crystals. Not because the universe is designed for consciousness, but because the same rules that create spacetime and matter also create the possibility of awareness. If this is true, then observers are not accidents. They are emergent features of a universe rich in structure, complexity, and information. And once observers exist, something extraordinary happens. The universe gains the ability to reflect on itself. This raises a profound question: does the universe require observers? Do observers play a role in shaping reality, or are they merely passive products of it? Quantum mechanics suggests that observation plays a crucial role in defining outcomes. But this does not mean consciousness creates reality. It means that interactions, measurements, relationships, shape how quantum possibilities become classical facts. Consciousness is one form of interaction, but not the only one. Still, the link between observers and reality is hard to ignore. The fact that the universe can be understood, that it follows patterns, that it can be described mathematically, that its laws are intelligible, is itself astonishing. Why should a universe built from quantum chaos and emergent spacetime produce beings capable of comprehending it? Some physicists argue that the comprehensibility of the universe is a clue. It suggests that the universe has a deep internal coherence, that the same principles giving rise to spacetime and matter also give rise to intelligibility. The universe is not random, it is structured in a way that supports understanding. Others argue the opposite, that comprehensibility is simply a selection effect. We observe a universe that can produce observers, therefore it must be the kind of universe that supports comprehension. If the laws were chaotic or incomprehensible, we would not be here to notice. Yet this argument fails to account for something important: the universe is not just comprehensible, it is elegant. Its laws can be expressed compactly. Its symmetries are deep and pervasive. Its behavior, though complex, is describable through equations of stunning simplicity. This elegance hints at something beneath the surface. Something that ties together emergence, information, consciousness, and geometry. Perhaps the universe is not just a physical system, but also a conceptual one. Perhaps reality is structured in a way that naturally gives rise to both the physical world and the minds capable of understanding it. Perhaps the emergence of consciousness is not an afterthought, but an integral part of the cosmic story. If spacetime arises from information, and consciousness arises from information, then the two may be reflections of one another, different expressions of the same underlying substrate. This brings us to an even more astonishing possibility: the universe might be self-referential. Spacetime emerges from information. Information emerges from relationships. Relationships emerge from interactions within spacetime. Consciousness emerges from information. Consciousness observes spacetime and discovers the laws that shape it. It is a loop, not circular, but reflective. A structure where each level informs and shapes the others. The deeper we look, the more reality resembles a self-consistent system, one where observers, information, and spacetime are inseparable. And this leads to the final, most mysterious question of all. If the universe is self-consistent, emergent, and deeply informational, then what gave rise to the first pattern? What ignited the process? What set reality into motion? To approach that question, our journey must now explore the nature of beginnings, where physics meets the limits of knowledge, and mystery begins. To understand the beginning of the universe, we must confront an uncomfortable truth. Our current theories, no matter how elegant, no matter how powerful, break down when taken to the extreme. Einstein's general relativity predicts singularities, points where density becomes infinite. And spacetime curvature diverges. Quantum mechanics tells us that infinities are signs of missing physics, places where our descriptions fail. The Big Bang singularity is the most dramatic failure of all. At the beginning, everything collapses: time, space, energy, matter, geometry. The equations that describe our universe at every other moment simply do not apply. It is as if the universe draws a curtain over its own origin. But physics refuses to accept a curtain. The human mind pushes back, demanding answers. What came before spacetime? What initiated the expansion? What ignited the first pattern of information? One possibility is that the universe didn't have a beginning in the traditional sense. Perhaps time itself emerged gradually from a timeless precursor, a state with no before or after, no progression, no change. In such a state, asking, what happened before the Big Bang, is like asking, what's north of the North Pole? The question simply doesn't apply. This idea appears in several quantum cosmology models, where time is not a fundamental backdrop but an emergent property of relational states. Before the universe expanded, there may have been no time, no space, just a cloud of pure potentiality. A quantum soup of possibilities, unanchored to any geometry. Another possibility is the quantum bounce, suggested by loop quantum cosmology. Instead of a singularity, the universe may have passed through a minimum volume, a tiny, dense state where quantum geometry resisted collapse. In this picture, a previous universe may have contracted before giving birth to ours. The Big Bang becomes the Big Bounce, a transition rather than a beginning. Yet another proposal is the cosmic inflation framework, which hints at something even stranger. Our universe may be just one bubble in a vast multiverse. If inflation is eternal, new universes may be forming constantly, each with its own physical laws, its own spacetime fabric, its own history. In that case, the Big Bang was not the beginning of everything, it was the local beginning of our region. The bigger reality may have no beginning at all. But even this raises deeper questions. What mechanism drives eternal inflation? What landscape of possibilities does it explore? What underlies the laws that govern its dynamics? Here, physics touches its limits again. Some theorists propose that the universe emerges from a quantum vacuum, a seething landscape of fluctuations where energy, space, and time spontaneously appear and disappear. The vacuum is not empty, it is a roiling ocean of probability. The Big Bang, in this sense, may have been a quantum fluctuation that did not collapse back into nothingness but stabilized into an expanding universe. But this explanation, too, leaves something unanswered. What defines the vacuum? Why are its fluctuations governed by quantum mechanics? Why does it have the structure it does? Other proposals take an entirely different route. Perhaps the universe is not a fluctuation, but a self-emerging informational structure. Perhaps the laws of physics arise because they are the simplest, self-consistent set of rules that can exist. The universe could be the ultimate minimal program, one that continues generating complexity because complexity is what the rules demand. Some physicists argue that the universe may maximize computational richness, or entanglement capacity, or informational efficiency. In that view, the early universe was not fine-tuned, rather, it was simply the natural starting point for a system seeking to optimize itself. Still others argue that the universe's origin lies not in physics, but in logic. That existence arises because non-existence is unstable. That a state of perfect nothingness is impossible, because even the concept of nothing implies a distinction, and distinctions are the seeds of information. In this interpretation, the universe must exist, not because of a cause, but because the absence of everything is logically inconsistent. These ideas are profound, but they also highlight how far we are from answering the core mystery: what set reality in motion? To push further, we must look at another problem that emerges from the beginning of the universe: why is the universe so uniform, yet filled with structure? Why do galaxies cluster as they do? Why does the cosmic microwave background show fluctuations of exactly the right magnitude to form stars and galaxies? These patterns appear almost designed, but they arise naturally if spacetime is emergent. If the early universe began in a highly entangled state, then the seeds of structure would be encoded in the entanglement. Patterns. When geometry crystallized out of this state, those patterns would manifest as density fluctuations, tiny variations that eventually grew into galaxies, stars, and planets. In this view, the structure of the cosmos is a fossil imprint of pregeometric entanglement. This idea ties the beginning of the universe to the deepest layers of reality. The emergence of spacetime and the birth of the cosmos become the same event. The Big Bang is not the beginning of time, it is the beginning of geometry. It is the moment when relationships became distances, when correlations became locations, when information became spacetime. And yet, even if we can trace the universe's earliest moments, we still face the largest mystery: why does anything exist at all? Physics may never fully answer this question. But by stripping away space, time, matter, and even laws, modern physics reveals something astonishing: the universe is not random. It is structured, patterned, self-consistent, and comprehensible. Its emergence seems to follow deep principles we do not yet fully understand, but which hint at a profound unity beneath everything. The beginning of the universe is not just a scientific problem. It is a philosophical, and perhaps existential, one. It challenges us to consider what origin means, what existence means, what nothing means. And it leads us, inevitably, to the final frontier of our journey. If spacetime is emergent, if time arises from information, if consciousness reflects the universe back upon itself, then what is the ultimate purpose, or meaning, of a universe like ours? That question awaits us next. When we ask whether the universe has a purpose, we step into territory that is both ancient and radically modern. For most of human history, purpose was imposed onto the cosmos, through myth, religion, or philosophy. But now, physics is circling back to a similar question, not out of mysticism but out of necessity. Because once we accept that spacetime, matter, and even the laws of physics are emergent, we must confront the fact that the universe might not be arbitrary. Emergence implies structure. Structure implies constraints. And constraints often hint at something deeper. But what could purpose mean in a universe like ours? If the universe is a computation, is it computing something? If it is information, is it organizing something? If it is a self-consistent structure, is it expressing something? If observers emerge naturally, is the universe predisposed to awareness? These questions sound philosophical, but they arise from physics itself. The more we uncover about the deep layers of reality, the more it becomes clear that the universe behaves as though it is driven by principles that go beyond mere randomness. One such principle is complexity. The universe begins in simplicity, a hot, dense, nearly uniform state. Over time, complexity increases, not uniformly, but dramatically. Stars ignite. Galaxies form. Chemistry emerges. Life appears. Consciousness blooms. Each step is a leap in structure, organization, and informational richness. Gravity helps shape complexity by pulling matter into clusters, quantum mechanics allows stable atoms, thermodynamics fuels life and energy flows. The laws of physics do not merely allow complexity, they seem to encourage it. Some physicists argue that the universe evolves toward states of greater computational depth. That information processes become more elaborate over time. In this view, observers are not incidental, they are part of the universe's natural direction. Complexity leads to awareness because awareness is the most efficient way for a system to model its environment. Consciousness is simply what happens when a system becomes sufficiently self-referential. This idea reframes purpose. The universe does not have a goal in the human sense. But it may have a direction, toward increasing complexity and richer forms of structure. Another principle is coherence. Quantum systems naturally seek coherence, states where information is correlated across vast distances. Entanglement, the very thing that might generate spacetime, is a form of coherence. It binds the universe into a unified whole. Even classical structures, like galaxies and ecosystems, show coherence at large scales. The universe does not fragment into isolated islands, it integrates. This suggests that unity is not accidental, it is built into the laws of physics. The universe evolves toward states where relationships matter more than individual components. If reality is fundamentally relational, then coherence is its natural expression. A third principle is intelligibility. The universe is astonishingly understandable. From the largest clusters of galaxies to the smallest particles, it obeys simple, elegant rules. Equations discovered in the 20th century still predict phenomena billions of light-years away. The cosmos is not chaotic, it is deeply ordered. Why should this be? Why should a universe arising from quantum fluctuations or emergent information follow mathematics so perfectly? One possibility is that intelligibility is a consequence of emergence. The only universes that can host stable structures are those with consistent, comprehensible rules. Chaos cannot maintain stars, randomness cannot produce chemistry, instability cannot produce observers. Intelligibility is not a luxury, it is a requirement. Some argue that this reveals something profound: the universe must be structured in a way that allows observers because only such a universe is self-sustaining. If spacetime emerges from entanglement, and observers emerge from complexity, then a universe without these properties would collapse or fizzle out. We live in a universe that is stable enough to understand itself. And this brings us to the most radical idea of all: the universe might be self-explanatory. Not in the sense that it has a conscious intention, but in the sense that its structure is shaped by principles that ensure its own existence. A universe with no order could not sustain itself. A universe with no law could not remain coherent. A universe with no information could not evolve. The universe exists because the alternative is not a universe at all. This does not answer the question of why existence itself exists. But it reframes the question: maybe the universe does not need a purpose external to itself. Maybe the universe's purpose, if we can call it that, is intrinsic, embedded in its structure, encoded in its dynamics, written into the rules that allow it to emerge from nothing. And if this is true, then consciousness, our ability to reflect, question, wonder, is not a cosmic accident. It is the universe recognizing its own structure. It is reality becoming aware of itself through the minds of the beings it produced. This idea is not mystical. It is the natural consequence of emergence. If information gives rise to spacetime, and spacetime gives rise to complexity, and complexity gives rise to observers, then observers close the loop by discovering the information that gave rise to everything. The universe is not separate from us. We are part of its informational architecture. Through our thoughts, our perceptions, our science, and our questions, the universe is effectively studying itself. Which brings us to the climax of our journey. We have gone from Einstein's spacetime to quantum geometry, from entanglement to consciousness, from the birth of the universe to the nature of meaning. Now, only one question remains. If reality is emergent, layered, relational, and self-reflective, then what does this tell us about our place within it? The answer lies just ahead. To understand our place in an emergent universe, we must reconcile two astonishing truths. First, we are unimaginably small, fleeting patterns on a tiny planet orbiting a mediocre star in a galaxy among trillions. Second, we are also the only known entities capable of contemplating the universe's deepest foundations. We carry within our fragile biology the capacity to reconstruct the laws that shape galaxies, decipher the behavior of spacetime, and imagine realities beyond our own. This duality is at the heart of our existence. We are insignificant in scale, yet profound in ability. If spacetime emerges from information, and information is woven into the fabric of everything, then we are not observers standing apart from the universe. We are expressions of the same informational structure that created stars, atoms, and geometry. Our consciousness is a continuation of the universe's unfolding complexity. This reframes the ancient question: what are we? We are not separate from the cosmos. We are not outsiders looking in. We are participants, nodes in the great network of relationships that constitutes reality. Much like spacetime emerges from entanglement, identity emerges from patterns encoded in the brain. Everything we experience, our thoughts, our memories, our emotions, are informational flows shaped by interactions. We are networks within networks, structures within structures, emergent systems inside an emergent universe. But there is a deeper insight. If spacetime is not fundamental, then location is not fundamental. You are not in the universe the way a pebble sits in a riverbed. You are part of the universe's relational fabric. Your existence is a set of connections woven into the larger structure of reality, defined not by where you are but by how you relate to everything else. This relational nature extends to consciousness. Your consciousness is not a light trapped inside your skull. It is a process, a continual interplay between perception, memory, anticipation, and interpretation. It is not confined, it is dynamic. It arises from interactions between billions of neurons, each shaped by experience, environment, culture, and evolution. And at the deepest level, those interactions arise from quantum fields and entanglement patterns that predates biology by billions of years. In that sense, consciousness is not merely in the universe. It is an extension of the universe's own informational behavior. But what about meaning? Does an emergent, relational universe allow for meaning, or does it strip meaning away? Some fear that if the universe has no inherent purpose, then our lives have no significance. But this fear is rooted in an outdated worldview, one that assumes meaning must be imposed from outside. In an emergent universe, meaning arises the same way everything else does, from relationships, interactions, and structure. Meaning is not given. Meaning is constructed. Meaning emerges. Just as atoms form molecules and molecules form cells, experiences form narratives and narratives form purpose. You create meaning because your brain is an engine of interpretation, weaving coherence from complexity. The universe does not need to hand you meaning, you generate it through your participation in reality. And there is beauty in this. Because it means meaning is not fragile. It is not dependent on cosmic intention. It arises naturally whenever a sufficiently complex system becomes self-aware. This leads to a profound idea: the universe does not need a purpose to matter. It matters because we experience it. It matters because we ask questions. It matters because consciousness illuminates its structure. In that sense, the universe expresses itself through us. Our curiosity is a continuation of cosmic evolution. Our drive to understand reality is an echo of the same principles that gave rise to stars and galaxies. We seek knowledge because we are made of the same informational fabric that shaped the cosmos. So what is our place in all of this? We are bridges between scales, tiny beings who can grasp the immensely large. We are local expressions of a global structure, patterns of consciousness capable of modeling the entire universe. We are temporary, but our understanding is not. The ideas we uncover transcend individual existence and become part of the universe's larger story. And that story is still being written. We stand at the frontier of physics, knowing that our current understanding is incomplete. We sense that something deeper lies beneath spacetime, time, quantum mechanics, and information. We know we are brushing against the edges of a profound truth, a unified picture of reality that humanity has only begun to glimpse. But this journey is not just scientific. It is personal. It challenges us to rethink our identity, our purpose, and our relationship to the universe. It asks us to embrace uncertainty, to value discovery, and to see ourselves not as separate observers but as active participants in the unfolding of reality. And now, after exploring the deepest mysteries of the cosmos, spacetime, entanglement, emergence, meaning, we reach the final step of our journey. A conclusion not of closure, but of perspective. A way to look at reality, and ourselves, with new eyes. The final part awaits. We began this journey with a simple question: what is spacetime? Einstein gave us the first great answer. He showed us that space and time are not separate, not absolute, not the rigid stage we once imagined. Instead, they form a living fabric that bends, curves, twists, and evolves. But as physics progressed, we realized Einstein's insight, brilliant as it was only the beginning. Quantum mechanics cracked open the universe and revealed a world far stranger than classical intuition could handle. And when we tried to combine quantum mechanics with Einstein's spacetime, the two refused to fit. They clashed, not because either was wrong, but because both were incomplete. That clash became an invitation. An invitation to dig deeper, to peel back the layers. To ask questions that undermine our most basic assumptions. What we found beneath spacetime was not more spacetime. What we found was information. Entanglement. Relationships. Structure without. Geometry. A world where space is not fundamental but woven from correlations. Where time is not universal but emerges from entropy, complexity, and interaction. Where gravity is not a force but a thermodynamic response. Where black holes are not endpoints but informational engines. Where the universe is not a place, but a process. As we explored these ideas, another realization emerged. If the universe is built from information, then observers, beings who process information, are not accidents. They are natural products of a universe that generates complexity. Consciousness is not an intrusion into physics, it is an expression of the universe's own structure. In that sense, our ability to understand reality is itself part of reality. The universe gives rise to minds. And minds give rise to understanding. Understanding gives rise to meaning, and meaning gives the universe a way to interpret itself. This self-referential loop is not mystical. It is emergent. It is the natural consequence of a cosmos where relationships matter more than objects, where information shapes reality, and where complexity evolves toward awareness. And now, after tracing this arc, from Einstein to quantum theory, from spacetime to entanglement, from the birth of the universe to the emergence of consciousness, we arrive at one final perspective. A perspective not of endings, but of clarity. In an emergent universe, nothing is fundamental, not even spacetime. But everything is connected. Everything participates in the same informational tapestry. You are not a separate observer. You are a node in the universe's great web. You are a pattern within patterns, a structure rising from deeper structures, an expression of relationships that stretch back to the dawn of existence. The atoms in your body were forged in ancient stars. The structure of your mind reflects the logic of quantum information. Your consciousness is the universe, becoming aware of itself through you. And that is the final, quiet revelation. We are the product of the cosmos, but we are also its witnesses. We are shaped by reality, but we also shape the story. We tell about it. We arise from the universe, yet the universe is incomplete without the beings who can see it, question it, and try to understand it. Einstein once said that the most incomprehensible thing about the universe is that it is comprehensible. But now we see why. It is comprehensible because we are woven from the same fabric we seek to understand. The cosmos made us. From its own logic, its own structure, its own information. And so, the journey does not end with answers. It ends with a new way of seeing. A universe where spacetime is not given but created. Where reality is not fixed but emergent. Where meaning is not imposed but discovered. Where consciousness is not separate but intrinsic. Where every question opens a deeper layer. Where every insight reveals another mystery. You are part of this universe, not merely living in it, but belonging to its deepest architecture. And as long as there are minds willing to wonder, the story continues. Not in physics alone. Not in equations or theories. but in curiosity. In imagination. In the quiet realization that, somewhere in the fabric of reality, the universe is still unfolding, and we are unfolding with it.